Hi everyone, welcome to the Seismic Data Processing course. In today's lecture we'll talk about what is the signal. So the waves that carry information to surface are called signals. These signals that instruct a device, that telling the device what to do. Okay. The waves carrying the information. What is the information? For example, about the subsurface, layers, and seismic exploration. This information is encoded in how the amplitude, frequency, phase changing with time. And we use the tool like oscilloscope or geophones to record these signals on the surface. So what is a signal? It is a wave that carry information, and we record these signals on the surface using tools. We have two different types of signals, continuous and discrete time signal. Continuous time signals, think about it like it is continuous, it exists at every specific period of time, is not a break. Example, in analog sound wave, so it's the same when we start talking, we send a continuous wave through the air, and this continuous wave is also called analog wave. Seismic vibration, when we have an earthquake, or voltage signals this is example of continuous time signal. Okay, it's also called the analog signal. It's continuous at and present at all of the time without any break. We have discrete time signal. Discrete time exists only at a specific period of time. It's called the sampling method. For example, we need to record a sampling after 0.1. So it's not continuous, is taken at any specific period of time. We also have periodic non-periodic signals. The periodic repeats itself after a fixed time period. So the same wave will repeat itself at a fixed period of time. Is example of the sine wave. The sine waves go up and down, up and down. This wave will repeat itself at any specific of time. And also you can consider it is the same as continuous signal. Non-periodic does not repeat over time. You have only one peak. This one peak is not gonna repeat over time. So example for that, random noise, a seismic signal from an exploration is considered non-periodic signal. Deterministic can be predicted mathematically. We use the mathematical equation, the sine wave equation, to determine the determination. But the random, we don't use any mathematical equation. This is unpredictable, varies with time in an uncertain way. So this is vary with time. Example, the background noise in real seismic noise. So why we are considering about the signal type? Because we need different tools and different analyze and process for each type of signal. For continuous, the analog, we use analog filters, amplifier, oscilloscope. If it's discrete, we use digital filters or algorithm. Periodic, non-periodic, deterministic, and random can be modeled mathematically, use statistical or probabilistic analysis. So for each signal type we have different type of tools and analysis to consider. Also you have to differentiate between signal and variables. Signals, the function that carry information. It change with time or space to represent something physical. But variables is a symbol or placeholder that can take on different values. It is used in mathematics or equation to represent quantities. So in simple term, what is the signal? It's something that exists and changes, like sound, vibration, voltage, or temperature over time. But what is the variable? It's just a name or label we use in the equation to describe that changes. For example, in the sine wave, in here we have the time. The time here is called the variable, and also we have A and F. A the frequency, and the A is also called variables. Digitizing of seismic signal. So the analog signal contains all the information from the ground but cannot be directly processed by computer. So we need to change the analog signal into a discrete sampling, so it will have the 0 1 value, so we can use it within the computer and we do our analysis. Each sample measures the amplitude. Each sampling in here measuring the amplitude per specific time, and separated by a sampling intervals, separated by the sampling intervals. So the DT sampling intervals is play a major role how we can take sampling each point. If we need to cover all the points one by one, very space, or we need to take very wide sampling intervals. So if the DT, the sampling intervals in millisecond, so the sampling frequency is called by 1000 dividing by the DT. If the DT is very wide, then the sampling frequency, it will be very low. That means we will not cover all the points. But if the DT is very close, that means the sampling frequency, it will be very high. That means we will cover all the points. That means we'll take the points like 1 point, 2 point, very close points. And now we have the Nyquist frequency. What is the Nyquist frequency? It's the highest recoverable signal. So it's like a default frequencies of the given sampling frequencies is given by. So the Nyquist frequencies is like a default value. Any value above the Nyquist frequencies is considered as low frequency signal, and we should cut this is low frequency signal. Equal to sampling frequency dividing by 2. So when you calculate the sampling frequency, you have to divide it by 2 to have the Nyquist frequency. And Nyquist frequency is like a default value. Any value, if the value above the Nyquist frequency, that means you have low frequency signal, and we need to cut this low frequency signal. So in here we have aliasing, digitizing error. What is the aliasing? In seismic signals, if the frequency component is bigger than the Nyquist frequency, that means these high frequencies will appear as false low frequencies. False low frequencies, the point will be very wide. Okay? In the digitized signal, this is called aliasing. So what is the aliasing? If you have the frequency component is higher than Nyquist frequency, this is called aliasing. What is the aliasing? It is low frequencies signals, and we need to cut these low frequency signals to remove the noise. We have high sampling rate, sampling frequency. If the sampling frequency is high, delta T for example is too low, that means this is capture the true waveform accurately. So high sampling rate, that means the frequency component it is less than the Nyquist frequency. That means you will cover all the signals. You will take the D time is very low. As we said before, when we have the delta T is low, that means we have high sampling frequency. If we have high sample frequency, we'll cover all the way. We will take one sample in here, two sample in here, three sample, 4, 5. It's like we are covering all the wave. We are covering all the wave. But if you have low sampling rate, the sampling frequency low, the dt is very high. If the dt is very high, we have low sampling rate, and that means we have, you can take one point in here, second point in here, third point in here. These are low frequency rates, and we need to cut this low frequency rate. And this is what is called the aliasing. So effect of aliasing on seismic data. Aliasing is a common problem in seismic processing, and it is usually associated with steeply dipping. So if you have flat surface, that means the dips is zero, but if you have a sliding surface like fault, you will have, like for example, 45-degree dipping. So depend on the dipping and the receiving distance. The receiving distance from, for example, this flat surface, or this is a sliding surface into the geophones. These are the factor that covering aliasing. So aliasing become a compromise between the frequency content of dipping events, the dip angle, so dipping events, the dip angles of the event, the trace spacing of the input data, and the aliasing noise content. So we need to remove all these noise, so we have very straightforward waves. Aliasing effect, as we said before, the Nyquist frequency is the higher frequency that can be correctly sampled for a given sampling rate. A Nyquist frequency is your default value. Any value above the Nyquist frequency is considered low frequency. We need to cut this low frequency. The false frequency is given by, this is how to calculate the false frequency, 2 multiplied by Nyquist frequency minus the true frequency, To avoid aliasing in seismic system, an anti-aliasing filter is used before sampling. So before sampling, we use anti-aliasing filter to remove the aliasing. This filter removes frequencies above a certain cutoff. So we set the cutoff. That's why the Nyquist frequency is very important. It's the highest frequency that can be correctly sampled. The highest point that we can sample. Any above that Nyquist frequency we will cut. Any value below this we are in the safe mode, but we can filter that by using the filter removes frequency above certain cutoff. Typically we use the aliasing frequencies, is called Fn divided by 2. So Nyquist frequency dividing by 2, that means only low frequencies below half of the Nyquist frequencies are recorded. This ensures no false high frequency energy fall into the data. So this is all you need to know about the thing. So thank you for watching, and see you in the next video.